Okay, thanks for welcoming us. So MIRAEX, we're coming from Switzerland, and I'm here to introduce you what we're doing in the microwave space and how we're a pretty rare company in the sense that we actually evolve and we deal with the full quantum ecosystem, whether it's sensing, whether it's quantum computing, or quantum networks. The pain that you will find in those three verticals are, well, linked to microwave transduction and make sure you can actually network any quantum resources operating in microwave domain to optical domain. So that's what we do, that's what we solve as a problem, and we're trying to solve this along those three verticals. So what we're doing there is we're building a photonic integrated circuit platform, which is patented, and it's dual use. That's important because that allows us to deal with both defense applications as well as commercial applications. So what's unique about what we do? It was actually, the patents were filed 3 years ago, applications were filed 3 years ago, and it came out this summer. And what's really unique about what we are offering here in terms of transduction is the fact that we're using a broadband approach. Everything that you will see academically anyway is based on either resonators or cavities that are extremely limited in bandwidth. And that's very important because when you're dealing, for instance, with defense applications, radars typically operates between 2 to 40 gigahertz. You want to be able to, with a single design, address all these requirements. So that's exactly what we're doing here. We have a design that can actually tackle 2 to 40 gigahertz frequency range with 1 to 2 gigahertz effective frequency range. So in other words, for quantum computing, this is extremely useful because when you're trying to do the transduction with qubits and actually convert them from stationary qubits into optical qubits that will be shared onto the optical network, you have qubits operating within a range of 10 to 10 gigahertz typically, and you want a single design to address all the manufacturers, whether it's IBM, Amazon, et cetera, et cetera. So in that respect, that is fully scalable. With a single design, we can address most of the customer's requirements. So where we are with our quantum interconnects and how we progress, which customers we talk to. So all of the major ones, IBM obviously being the market leader there, Google, Amazon, Microsoft, and we're speaking to Intel next week. On the defense side with sensing, we had really good contacts with Lockheed and as well as BAE. I was in Merrimack on Monday. And Hensoldt, we've got some funded POCs that was going to be starting in February next year. And we actually have ordered from Melter System in Israel for a feasibility study for the quantum radar application. The big market and what we're targeting in the end is entangled networks, basically. So there we've got the potential 50% serviceable market with quantum repeaters. So quantum repeaters are typically the grail every government is after because this is a potentially single communication channel enabling the safe communication and also global entanglement of quantum resources over the network. So how do we get there? So we've got critical milestones on our roadmap. Next year is mainly transducers and what we call classical interconnects in the sense that they actually do not perform a full quantum coherent conversion between microwave and optical photons. But they do actually use to enhance radar performance detection, as well as providing some potential photonic links for quantum computers and simplifying the coaxial connections down the Dilfridge. We've got the Startup Innovation Program that started in July this year. That's a 3.4 million funded program by the Swiss government to actually build and provide those MVPs, a quantum interconnect in 2026. And 2026 is critical for us because we hope to reach operational profitability by then. And we will need some support to go potentially to and achieve our moonshot, which are the quantum repeaters in 2028. And this is where we need you guys. So most of our clients, if you've seen on the slides, they're based in the US. So what we want to do is have a strategy, a development strategy, where we can actually have a lead investor that will support us in supporting us in the long term, because quantum is going to require long-term support. But also for the short term, enable us and open the door with the defense prime contractors. And finally, achieve some more financial leverage with national initiative grants like the Swiss one. So we've got two choices, one on the right, one on the left. The one on the left is the one I prefer, i.e. a quick entry, Q1 2024, with a preferred seat on the table, on the shareholder tables. That's pretty much it.
Thank you. I have three quick commercial questions. One is, do you have revenue? Two is, are there any, outside of the customers you mentioned on the slide, are they going to be quantum companies or any other types of commercial customers? So I'll let you answer those quickly.
So we're going to start with defense companies. So yes, we have revenues this year. So we have paid orders from ELTA in Israel. And we were supposed to close a deal about 1 million with them end of last year as part of an offset program. And that unfortunately actually switched to, 2024. But yeah, offset programs is a great way to achieve, regular revenues, especially on R&D.
The last one was also, how are you making money?
Well, the long term is, so first of all, the transducers, they're less complicated products compared to the quantum interconnect. So we could make these generic products really quickly. So we have POCs in 2024, and we hope to roll them out, just after that.
So thank you, Daniel. I heard you mention profitable by 2026,
Yep.
if I heard that right. And I'm curious, why would it take 3 years to be profitable? Is it high cost of goods? Can you not charge enough? What is it?
So what we're developing is a photonic integrated platform. If you go to a foundry and you go full active run, it's 100K, just to try. And then there are plenty of iterations, to reach actually the state-of-the-art performance that we're after. In order to perform fully quantum coherent conversion, we need to reach 50% conversion efficiency on our devices. So this is what it takes typically to get there.
Thank you.